Welcome to the Friday Smart QA Musings, which is a gentle flurry of interesting thoughts. This particular Smart Musings was probably due to the recent the air crash that we had, a sad one. And that got me thinking, those kinds of accidents and investigations are pretty serious, deep. What can we learn? Of course, the idea was to look at it from a system, and therefore today's discussion on Smart QA Musings is air crash investigations and systems thinking in QA. Hopefully it should be a very interesting one. What I've tried to do is to piece in the typical notions of system thinking mindset, and then connect some of the air crash investigations and how certain system thinking mindset probably was more on top. It's not that one of those mindsets is what is applicable to that particular accident. So we'll probably go through that. Of course, an air crash investigation is pretty serious stuff, probably sometimes causing lots of lives, and certainly has a major business impact too. What can they teach us about systems thinking? We all test software and systems and assure and so on, but what do we mean by systems thinking? And how can, therefore, failure analysis lead to a more resilient assurance? You're thinking more smartly, so to speak, right? That's the idea. Air crash investigation is a very rigorous form of failure analysis because this occurs after, unfortunately, the accident. And we all know that a failure is really a confluence of factors. There isn't really a singular cause most often. And it's fairly complex, and that's why it takes a lot of effort and a lot of intelligence to figure out and then hopefully learn from it so that we can prevent. And therefore, the focus really is on learning, on prevention, and certainly the improvement of the overall system of how we build the aircrafts, how we follow, how we adjust processes, and so on and so forth, right? And therefore, this particular discussion, musing, is really about how can we apply some of the principles that they do into what we do. Before we jump along, let's just take a look at what systems thinking is really all about, right? I'm sure we have heard that term. Some of us practice it. A fairly interesting term, a fairly serious discipline, systems thinking is. In a nutshell, you may think about it in a simplistic form as a holistic approach to problem solving that emphasizes understanding of different parts of a system, how they interact, how they influence each other to produce an overall behavior. Because system, by definition, is a fairly large, loose word. What constitutes a system is not just equipment. It is the entire paraphernalia, the equipment, the people, the process, the environment, and so on and so forth. So the idea of seeing the whole, from engaging different perspectives, seeing different points to leverage, looking for relationships, looking for consequences, and thinking not linearly but circularly, understanding and embracing, if you will, the notion of complexity, the interconnectedness, and finally constantly questioning assumptions. Those are the eight thinking mindsets that possibly constitutes systems thinking at large, whose objective is really going beyond analyzing the individual components to considering relationships, interrelationships, and the feedback loops, because nothing is independent. Something affects, it gives back some signal, and then we respond, we don't respond, we ignore it, cascades, and so on and so forth. And therefore, this approach of thinking is hopefully to identify root causes and problems and develop more effective, sustainable solutions. So keeping this picture in mind, and of course correlating it and seeing it from the context of various accidents, and then trying to see what it means in our context of testing. That's really the approach. So let's look at, in a way, what are system failures? System failures by definition are, as we talked about very briefly, are complex. They are layered. They could arise out of physical components. They could arise about, software logic. It could arise, out of human actions. It could be arising of certain processes. In the context of aircraft, it's probably training, the processes, practices at an organization level, and so on. So there is a serious set of layer that's up there: components, the driving logic, and the people, and the processes and practices. Right. In a similar context, when you look at it from software, I think we can see that very crudely in terms of infrastructure layers, in terms of team practices, release hygienes, humans who interact with the system, and so on. So failure occurs across all these layers, just to kind of set the context. Hey, software system failures are not singular. We all know that. So let's now kind of go on to the matter of interest in terms of looking at what can accidents and therefore the air crash investigations possibly teach us. So all I'm going to do is to kind of take some accidents which I've got culled out from the web and try to correlate to some of these ideas and see what they possibly can teach us. So there are about 8 of them that I have, and I'm just going to kind of walk you through in a storyline fashion across each accident, probably take maybe a couple of minutes, and hopefully we'll be just around time. Some of you, I'm quite sure, will be able to relate to some of the accidents, fairly serious ones. So this was an accident that occurred in the year of 2009. It was involved Air France. The story is, there was a scheduled flight which is going in from Rio de Janeiro to Paris. Obviously, it's a lot of ocean, as you can see, right? And I'm sure you might remember that it just vanished into the ocean. And it took many years to figure out what the heck happened. What really happened was possibly there were some inconsistent airspeed indications and miscommunications, and it ultimately stalled the Airbus 330. They failed to recover from the stall, and it crashed into the mid-Atlantic. And that's it. Now, obviously, a major amount of investigation occurred. It just fell into the sea. Quite obviously, as you know, everybody died. Now, in summary, what it seemed to, ultimately, after all these investigations, they found that at cruising altitude into turbulence, and pitot tubes, which actually measure pressure, as you can see those airplanes, you find those little tiny things that are jutting out of a plane, the pitot tubes, they froze. And they fed bad airspeed data. And the autopilot disengaged. And of course, a lot of confusion in terms of data that was coming into the pilots, and leaving the crew to interpret conflicting cues in terms of what their speed is. And they were under stress, remember. Quite obviously, this combination of failing sensor, misguiding cues, stress, it led to a fatal stall, and it cascaded. And then, sadly, the plane fell down. A cascade of confusion and unpreparedness, right? So this is the story of this particular accident. So what might be something that we can discern from here? Obviously, a lot of them would be applicable. I'm not saying that just this particular thing is applicable. I think what I've tried to do is to pick something that is relevant. Nonetheless, the other things are also equally important, equally do play a part. The lesson number 1 from this particular accident is systems are more than just the components. It's not just blaming the pitot tube and saying, hey, it froze and therefore it goofed, so let's fix the pitot tube. Each of these accident investigations, if you go look around, is a fairly detailed investigation stuff that's up there. But in summary, what it seemed to indicate is failures involve sensors, in this case the pitot tube, human inputs in terms of what it gives, and there are different tubes, different speeds. There was confusion and that stuff. The notion of automation of how it is displayed, and weather and stress and stuff like that, right? So the point is, are we able to see the whole picture? Are we able to see the whole picture and hopefully do something about it? And that's the learning from this particular lesson. It's not just a singular failure. It's a combination of many, many things. And unless we see the whole picture, it's kind of hard to figure out what to do. So takeaway, very crudely put in the context of software, is look, when we test, we're not testing a piece. We are testing a series of interactions across many, many layers, as we briefly talked about. It could be layers in terms of UIs and APIs and infrastructure. And it's not just about individual layers, features, so to speak, right? So that's one simple way to kind of look at learning from this particular accident, where we see the system is far bigger than the sum of the components. The another accident, which occurred in 1978, I think this occurred in the US mainland. It was a DC-8 plane, which was approaching Portland Airport in Oregon. What happened was there was a landing gear problem, so it didn't retract properly, right? And the crew members were trying to figure out what was wrong with the landing gear. Why didn't it come down properly? And so, as a part of this, exercise of debugging, they decided to hold a pattern around the plane, and then they were holding pattern near the airport until they fixed or figured out what to do with the landing gear. Right? The crew became preoccupied with this landing gear indicator and somehow lost awareness that they were actually blowing up fuel. The fuel was burning, right? Because they were doing a holding position. The flight engineer, who was much younger compared to the main commander and the pilot, never really spoke up about the fuel situation because the captain was busy trying to figure out about the landing gear. When the co-pilot and the pilot realized that suddenly they were low on fuel, they declared an emergency and tried to land. But then the fuel was done and they crashed, right? And luckily, they did crash. Not the entire 181 people died. About 10 people lost their lives. Right? So what does this kind of teach us? Events are surface clues. Be careful about the consequences. Right? So there is an event, in this case, landing gear, you're preoccupied with the problem. But, you put in the holding pattern to debug the problem and figure it out. But then you somehow in the entire process lost count on fuel. And the person who was tracking fuel did not feel courageous enough to probably tell that, hey, Mr. Pilot, fuel is running off. And therefore, the consequences was pretty, difficult. They were just looking at surface clues. So very crudely put, it's like saying, hey, there is a bug, but then I think the real stuff is what's the deeper diagnostic. It's not just the fix, right? And that's what we're trying to say. The interesting thing that occurred to the industry at that point in time, which also was noticed in the healthcare industry, was the fact that when, in this case, a pilot who is a very senior, experienced person who commands the plane, and then there is, the younger person who probably is much younger, there is always a difficulty in the younger person speaking up to the pilot. And this was one of the reasons why the co-pilot didn't seem to highlight to the captain that, stop it, you're running out of fuel. Happens in hospital industry too. It used to happen in the hospital industry too, healthcare industry, as in terms of nurses not speaking up against the doctor when procedures are not going well. In the case of the aircraft industry, that resulted in what is called as a crew resource management, where the United Airlines was the first to use it in 1981. What this is about teaching the captain, co-pilot, and crew members to communicate effectively during flight, so that there are less errors and more efficiency during crew members. Why? Because, differential maturity, right? And therefore there is a sense that it would be considered inadvertent to talk to a senior, right? And that's an interesting learning. And this was put up in 1981. Now it's practiced. In fact, the same crew resource management came in very handy in another major failure, major accident. Okay. Let's look at the third kind of stuff. So we moved from seeing the context to seeing the consequences, and let's look at another accident, which is an Asiana flight, where with 307 people on board, it was flying too low, too slow during a landing attempt, and therefore it struck a seawall and was ripped off, and the rest of the plane went spinning and sliding down the runway. Right? So what happened? What the NTSB, the National Transportation and Safety Review Board, Chris Hart at the time, the acting chairman, said that increasingly complex automated aircraft controls designed to improve safety are instead creating new opportunities for error. The Asiana flight crew over-relied on automated systems, and they did not fully understand. In their efforts to compensate for the unreliability of human performance, the designers of automated control systems unwittingly created opportunities for new error types that would be more serious than they were seeking to avoid. That's pretty interesting, isn't it? That we kind of over-engineered and in the process. So human factors are central. So here what happened, the equipment is too complex. And that particular stuff. So I think also in one of the book called Checklist Manifesto, they talk about the fact the plane is, of course, in a different context, in a different plane. The plane is too complex for one human to fly. And therefore understand failures are not always from technology, but how humans interpret and central to it under stress. And therefore we need to engage from different perspectives. And so the understanding of human factors in a situation become very key. And therefore, when we test, are we reflecting as much real world human behavior, distraction, fatigue, reliance, automation, etc., not just ideal paths. So how much are we adding into our system of tests, where we are looking at it not from the system as in terms of the software or the product, but the larger context, right? So in this particular case, the system was just too complex. So it took over a few things and you couldn't do, and so on. There was also another accident, I think if I'm not mistaken, that was somewhere in 89-90 in Bangalore. And that was the 330, I think, the Airbus 330, which was the fly-by-wire technology. Then it crashed into the Bangalore airport, the wall actually. And that's because they kind of somewhere misjudged and they hit the wall, and that was pretty fatal. In fact, a friend of mine passed away in that, as a classmate of mine. Why? Because, the technology was a fly-by-wire, so it took over control from you and you couldn't get back the control. So I remember very distinctly for many, many months, the aircraft, the 330 series were grounded by all the Indian Airlines then. Right. So another accident in 1989, which is United 232, which where this aircraft was going from Denver to O'Hare in Chicago, and it crash landed at an intermediate airport because it couldn't go all the way. And why? Because it lost its tail engine. And why did it lose? It lost the complete hydraulics, and only half of them survived. So the tail engine imploded, shrapnel severed all hydraulic systems. And if you know, hydraulics are very, very key to maneuvering a lot of these parts of the plane, and something that at that time was thought impossible. That crew did manage a partially controlled crash landing because they didn't go all the way to Chicago, but they went into a Seahawks. And the investigation team did praise the team and drove systemic improvements without finger pointing. In fact, I think if you search the net, you will find a lot of information about it. In fact, I think the pilot, though seriously injured, I think died many, many years later. And I think there are a lot of videos about him too. So what are we talking about? What's the system thinking mindset? Thinking circularly, not linearly, because we are not trying to blame anybody. We're trying to do blameless postmortems in this particular case, investigations where they are focused on learning rather than blame, by thinking from all many directions, which is circular thinking, so to speak, so that we can create a lasting impact. So I think, at the end of the day, we all know that issues occur, bugs happen, failures occur on the field, and there are obviously certain finger pointing that always occurs to the person, to the system of, collection of people and so on. But the question is, how well are we able to adopt to a blameless post-mortem as much as possible so that we can do continuous learning, codify these learnings, and close the loop continuously, right? Yeah, half of them died, but then half survived in this particular case. It's a fascinating story if you read the full piece on UA 232. In an accident that occurred from a regular scheduled flight from London to Sydney airport, took off from Changi airports. And after some time, the Airbus 380, it suffered an uncontained failure in one of the 4 Rolls-Royce engines, the Trent 900. This failure occurred over one of the islands of Indonesia, Riau, about 4 minutes after it took off from Singapore Changi airport. After holding out for nearly 2 hours to assess the situation, the pilot did make a successful emergency landing back at Changi. Interesting thing, no injuries occurred to the passengers, crew, or people, despite some of the debris of the aircraft falling onto the houses in Indonesia. What happened? An engine exploded after takeoff, triggering a cascade of failures. The well-trained crew used structured checklists and improvisation to land safely. Their preparation turned a potentially catastrophic scenario into a controlled emergency. What do we learn? Leverage, right? Simulate. In this particular case, they did a lot of simulation-based trainings. I'm sure we all know that they do a lot of it. And that's what helped them to anticipate and take care of probably a very serious situation. So training for failure probably enables calm, confident actions in the face of chaos, right? So accidents happen. Question is, how do we treat it? So how do we build resilience, into what we do beyond the ideal states, anticipation, stimulation, and adaptation. And therefore, one of the thinking mindsets here is probably seeing new leverage points by, hopefully, in terms of anticipation, by probably preparing for it via simulations and trainings and so on and so forth. Interesting that and it's nice to know that here is a situation, despite a fairly serious stuff, life was not lost. A pretty sad accident, which occurred in 1996, which was a value jet, which at the time was a bit of not the best of the airlines. They were cheap and there were safety compromises, as this investigation pointed out. But it was on a regular scheduled flight from Miami to Atlanta. And it just crashed en route into the Florida Everglades 10 minutes after departing. All the people died, 110 people. And some of you might have read it, you might have known that this Everglades accident. Why? They found that the cargo compartment did contain oxygen canisters, which were mislabeled. Now, oxygen canisters are a problem because they can lead to fire. Well, it led to total system failure. And subsequently, they did find out that prior warning signs about cargo fires were ignored. And what really this disaster showed is if prior faint signals or warnings were ignored, and they resulted in a catastrophe. So the lesson number 6 is watch for weak signals, right? So spotting on weak signals can prevent main failures, right? So weak signals could be SLA defect, something happened, it was not catastrophic yet, but they're subtle. But at a particular situation, they connect on to various things and then they cause a catastrophe. And therefore the system thinking mindset is look for relationship. It's not just about, here is a weak signal. You look at the larger context, how it could possibly connect on and possibly cause much bigger issues. So early signs are probably not something that we can casually ignore. We all know that it's probably a reiteration. The last but one of the accidents, which was crazy actually, but it's really sad. On February 6th of 1996, a 757, it crashed shortly after takeoff from Luke Perron International Airport. All 189 people died. Again, it was a pitted tube problem of showing incorrect speed. But what was interesting about it? The aircraft was sitting on the tarmac for 20 days without flying, and therefore they found out that a wasp had built a nest on the pivot tube, and obviously the pivot tube was not functioning well, and all due to a wasp building a nest. Well, the plane crashed. Again, conflicting data, timely cues, etc. The breakdown wasn't mechanical, it was informational, right? What does it mean? Feedback loops were probably ignored. Maybe there were some initial feedbacks, but they were not taken into consideration. We have to understand that embracing complexity, which is a very interesting thing of various connections, various loops, and so on, are a challenge, right? And ultimately they found out that yes, it was the wasp. But then, the pitted tube caused a lot of confusion, so to speak, and those feedbacks were probably not taken into larger consideration. And the last of the accident, which was the Lion Air flight, which I'm sure you might have heard, which were about a plane which took off and so 737 MAX, right? At that time, that became the infamous MAX later, because it was the second plane which just went into the ocean. It was going from the western city of Pankal to be, it was a flight JT760, 7610 Lion Air. No sign of survivors. It took many, many years to figure out. The designers assumed that the pilots could identify and override an automated MCAS behavior. MCAS was one of these automated computerized systems. But these assumptions were never validated in training, and the aircraft crashed due to a chain of decisions, not validation. What does this tell us? They assumed that people could take over and people could understand and do some stuff with a complex automated control system. And that assumption turned out to be fatal in this particular case. So all it simply tells you is question your assumptions. Testing assumptions is probably key, to an hypothesis, so to speak, based assurance. And what was the assumption here? That, well, it's the complex system would help, and details I'm not kind of sharing in great detail now. But the point was it is a complex control system. And certain assumptions were made, but not right when it came to actual usage and interpretation by the pilots. So some of the insights that maybe, if you were to summarize as the last slide as to what could be some of the insights inspired by ACI, I'm sure there is many, many more. It's just a small drop here, what we are discussing. The idea of deep root cause analysis, to probably figure out origin tracing in a much more deeper fashion. Understanding that layered approaches of interaction and probing is fundamentally necessary. Focusing on the fact it's not about the machine, it's not about the human, it is about, knowing humans' interaction under the situations, maybe under different stress, different environments, different ambiguity is paramount. Post-mortem, yes, we all like to do retrospectives, post-mortems, whatever, but the question is how well can it be blameless? How can we convert that into meaningful improvement actions as best as possible? Yes, there are human failures, there are machine failures. We all know that, right? Yeah, how can we practice? What can we simulate? What can we train for? And therefore, how can we look at certain scenarios better when it comes to the act of uncovering? In the indicators matter. Sometimes you might find a silly issue. Sometimes you might find a situation which comes up and it goes away. But then the question is, are we paying attention to signals, possibly the weak ones also, and worry about some of the side effects? It may not be always be fatal, but it's imperative not to ignore weak signals. The feedbacks, we all get feedbacks from the system, from people, from practices, and so on. Are we monitoring? Maybe it is deployed and we get some feedback from customers, from users, from whatever. How well are we able to monitor and loop it back into the system and take care of them? And finally, of course, challenging assumptions. So construct in terms of hypotheses and proof, and constantly do that as best as possible so that we are assuming as less as possible, right? So aircraft is indeed tragic, and hopefully every investigation makes flying safer. The most recent accident which occurred on our soil here, tragic however it is, again, people say that, look, it is still much safer from a statistical point, but statistics are different. The guy who loses somebody understands the pain, much like the defect in production is frustrating to the guy who actually built and tested the software team at large. But each of them holds really a mirror. And it's hopefully our objective, our larger objective is not just about finding bugs, it is about preventing disasters. With that, let me conclude and say thank you.